Today, I'm together with the distinguished colleague, Dr. Tuzun, and our topic here is performance-based seismic design. This will be an overview of performance-based earthquake engineering, and we will talk about the history, philosophy, feature, and examples from the engineering practice. Personally, I really can't wait to hear what Dr. Tuzun will deliver today. I'm sure I will benefit a lot from it. But before that, I'd like to briefly talk about Prota. Prota Group was founded in 1985, and we are now a global software development, engineering, and consultancy group. As you can see on the map, we are an expanding company and we are growing every year. Today, we operate with more than 15 offices located in Malaysia, Singapore, Philippines, Poland, and Turkey. Besides our regional offices, we support our customers and provide services through our channel partners. We have 16 partners across Europe, Africa, Middle East, South America, and Southeast Asia. So as structural engineers, what do we do really? As you are well aware, as engineers, structural engineers, we wear multiple hats. We model, first of all, we model the real life structures with BIM objects. So we try to model real world scenarios with loading, materials, and physical properties of the structure. Then we do the analysis, finite element analysis of the structure. Then we perform design according to the codes of practice. As you know, structural engineering practice is quite fragmented. So in every country, while we conduct our engineering business, we have to comply with different codes of practice. So that's one challenge that we are facing as engineers. And also we create detailing. Again, this also changes from practice to practice. Some of the engineers are not responsible for delivering the detailing, but most of us also create detailed drawings. It can be a reinforced concrete detail or steel detail. So that's also part of our job. Or also creating detailing, maybe adding additional value to our business as well. And also, as an additional value, we are even asked to create fabrication details and constructible information. Even though there are dedicated fabricators and dedicated draftsmen to do this, most of the time this can be the part of our business. And also we coordinate and share project information through BIM. So these are all the hats we are wearing. So here you see our latest technology solutions that we offer for the market. ProtaStructure is for modeling, analysis, and design of building structures. ProtaDetails is for automated RC detail drawings, reinforced concrete detail drawings. You can create all RC details of the building designed in ProtaStructure with only one click. ProtaDetails also includes intelligent rebars and design libraries, such as retaining walls, scaffolds, piles, pile caps, swimming pools. We can create design and detailing documentation of all these components independent from the structure. ProtaSteel is our latest technology for steel detailing and connection design. General arrangement drawings, assembly drawings, part drawings, numbering, clash checks, connection design, manual user-defined connections, all the features that you need in a typical steel fabrication software is a part of ProtaSteel. It also supports IntelliConnect to intelligently connect the members together by assessing the joint situations. And finally, ProtaBIM is our BIM platform that we can link the models with other BIM platforms, including Autodesk Revit, Tekla, and other industry-leading solutions that you may need to share data. Now, before handing over to Dr. Tuzun, I would like to briefly introduce him to you. Dr. Tuzun holds a PhD degree in earthquake engineering in Kandilli Observatory and Earthquake Engineering Institutes in Boğaziçi University. Dr. Tuzun has worked in the same department as a senior researcher from 2007 to 2017 and participated in national and international projects related to earthquake engineering. Dr. Tuzun is acting as an expert consultant in structural earthquake engineering and working as a part-time lecturer in Gebze Technical University Department of Earthquake Engineering. The research fields of Dr. Tuzun can be named as urban seismic risk assessments, performance-based design of structures, seismic design of isolated structures, seismic design of high-rise buildings, seismic assessments, and retrofit of existing buildings. Dr. Tuzun, audience is yours now. You can share your screen whenever you like.
Okay, thank you very much again. Good morning, everybody, and good evening or good afternoon for the participants from the east side of the world. Thank you very much for this opportunity to share my limited experience in earthquake engineering, and thank you for the introduction, Mustafa. Today, I'd like to talk about performance-based seismic design of structures. As Mustafa mentioned, I will talk a little bit about history. What was the history of so-called performance-based earthquake engineering? What is this philosophy? What we are doing now? What we are heading in the future? And some applications from engineering practice. Before starting, I want to emphasize that as a civil engineer, we are more focused on what we are doing than why we are doing. Today, I'm going to talk about why we are doing this, what's the reason of this approach, what's the reason of this procedure, rather than what is the detailed applications. In fact, performance-based design started for many decades ago. You know, the code of Hammurabi, the design criteria was defined already by him. And as you know, or as you see, if the house has built falls and kills the householder, the builder shall be slain. This is the very basic, or the very general performance criteria. This means that the building that you have constructed or designed should withstand all actions. Otherwise, it's the end of the building will be the same of yours. Nevertheless, and you all know that we are structural engineers, the very famous quota that we all know. We are using materials to build structures and to withstand forces. And we say that, okay, our responsibility has been achieved. But we all know that we don't know the properties of the buildings, that the materials that we are using. Even we can't analyze the buildings exactly. We do approximately and using some assumptions. And we don't know the forces, which was not accurate, you know, even the dead loads. let alone the lateral loads like earthquake forces or wind forces. And one thing I want to emphasize within this webinar is that we are all making a process based on probability, based on unknowns, based on approaches, based on assumptions. But up to now, we have a general approach or general tendency in design of the buildings, which is so-called prescriptive. We have so many codes in different parts of the world, and they provide a kind of prescriptive methodologies, prescriptive rules, which is simple to design or very straightforward and simple to check and simple to be economical. And since we are doing the same thing over and over again, it's not a kind of reinventing the wheel on every project. But by the time, by the practice experience increased, we have some problems in the prescriptive approach. What was that? In a way, the loss of ability of change, because as we follow the same things from the first day, nothing changes. We should change our minds. And of course, we should introduce some innovative technologies and provide some economical gains in our designs. But in prescriptive design, it may be lack. Of course, it should be have some compliance with the other sectors and other parameters, but in prescriptive design, you may also have lost this. And what is wrong with the performance standards? In seismic engineering or structural engineering, we sometimes do quantitative, sometimes do qualitative approach. In terms of quantitative criteria, we want to define something in quantitative fashion, but sometimes it's quite difficult to develop, or even often too difficult to achieve a consensus between engineers. For instance, in classical seismic design approach, we say that the performance of the building will be life safety under severe earthquake. This is a definition in almost every code, but there is no kind of quantitative criteria. What is severe earthquake? What is life safety? This is something that we know intuitively, but we cannot say, okay, it's a defining by a number, defining by a parameter, but just we say some round words. And additionally, evaluation process is not that much meaningful, because since you don't have a definite criteria, to evaluate the design or evaluate what has been done is in some way debatable, or in some way not easy to have the same consensus. You may provide some measures in terms of analytical approach or experimental, but even it is not that much easy to say the right parameters. Starting from 1970s, several approaches or several standards has been introduced in main countries like US, and they provide some performance criteria documents for different types of buildings and different types of facilities. But of course, these are so limited. But after 1975, with the National Institute of Standards and Technology, this documentation and this approach was evaluated, evolved from documents to codes and standards. And of course, in all documents, or in all of these documents, intend to achieve a performance. at that time, or at that the initiative was based on to protect the public safety. That was the main perspective. Of course, not only the natural hazards, but the all kind of hazards were included, like fire, or in case of any structural collapse, or even spread of disease. At that time, even that was a big problem, because after big disasters or big collapses, not just the building itself, but the system or the infrastructure may be affected and affect all the community. Of course, there's another criteria, the comfort of the occupants in terms of noise and vibration environment. All these involve the so-called performance, because as civil or earthquake engineers, we most focus on seismic safety, but I will just go in detail. But serviceability and durability is also important factor for the performance. We should not focus on performance just for seismic actions, but also the other factors that I'm going to talk about in the coming slides. And we know that starting from the so-called building code, the Blue Book times, the most building code provisions are not performance-based. They intuitively believe that they are capable of attaining desired performance. Intuitively, as I mentioned, this is not a exactly defined, quantitatively defined performance. And at the end, after every earthquake, after every seismic event, we go to site and see the result and update what we have done. And designers who follow these codes just know the rules, but they don't know what rules are required. They don't understand what is the performance, and they have no capability of adjusting their design to change the performance. In most cases, even now, like I have the experience in Turkey, but probably similar situations may have in other parts of the world. Engineers think that once they know the rules of the code, they are good designers. Of course, we should follow some minimum standards or some procedures, but the more important or the critical issue is the designer should know its building's behavior under these loadings or under these actions, rather than knowing the minimum reinforcement ratio or minimum dimensions and other code requirements. And once we change our mind to performance-based design, the designer should understand the performance, in a way, how the building will behave after the expected seismic action. And what is the design criteria or design rule that will result in which performance? What is the design procedure followed in a shear wall design, and what is its reflection to the overall performance? They should link this design information to the overall performance. And of course, they are forced to predict the expected performance to a given design event. And since the classical design is based on just one seismic level, but as a performance-based engineer or engineering application, we should consider different levels and different behaviors. And all these informations has been gathered from 1975 to 2000. And in year 2000, everything has, in every so to say sector, or every thing has produced a millennium version, so-called the Vision 2000 or millennium approach. And in California, the Structural Engineering Association of California has introduced the very famous performance-based design philosophy, and they introduced the very famous matrix that relates the building behavior with the earthquake design level, or the earthquake input level. What is wrong? What is the reason for that? There are many reasons, but the basic reason was the current code was just dealing with the single performance and single event, and the analysis was linear, and then, although we know that the structures will respond nonlinear inevitably in seismic actions, we are trying to reflect this behavior through some factors like seismic load reduction factors, or other R factors or Q factors, and try to simulate, or try to find the nonlinear response. Of course, this was not that much acceptable or that much efficient, and additionally, since every area of the world has different seismic design or design philosophy, design approach, design practice, seismic input level, and so forth, we should introduce something local rather than global approach. What happened? The very famous Vision 2000 produced the FEMA 273 and ATC 40, and about 20 years ago, 25 years ago, they introduced the performance levels in a descriptive manner rather than general or round definitions, and they have linked the performance levels with different seismic hazard levels. And again, qualitative and quantitative measures has been introduced. And as I mentioned in the first slide, everything has uncertainty, starting from the loads, material qualities, analysis procedures, analysis assumptions, and so forth. Uncertainties has been introduced, and the implementations were done forces and the deformations. Not in previous approach, engineers were doing their design based on demand and capacity ratios, so-called. All the design process was based, most of the times, based on forces, but now we changed our mind to deformations. As I mentioned, it started in mid-1970s, ATC3. It's first time the strength-based design has been introduced, and Vision 2000 laid the fundamentals of the performance-based earthquake engineering. The ATC 40 project and a FEMA 273 and 74, it was the practical implementations, because you may have good approach, you may have good ideas for design, or you may have good theoretical basis, but it should be practice oriented. Otherwise, if you do not apply your approach or methodologies in the practicing engineering society, it makes no sense. That's why ATC 40 has is a kind of milestone that it was introduced to practical engineering design process. And FEMA 358-56, first time it was codified, and then it all started after USA. It extended to Europe with Eurocode 8 in 2005. In 2009, it was in Japan, and first time the code involved performance-based assessment in Turkey was the 2007 code. It was just for assessing the existing buildings, but we had updated our code in 2018, and the performance-based design procedures is also applied for the new buildings. As I mentioned, the consideration was based on different tiers, basically 3 different earthquake intensities, different performance definitions. The details are defined in terms of forces and deformations, as I mentioned. And it's what we do, we basically relate performance with earthquake probability. What is the probability of our earthquake that we are expecting in that location, and what we are expecting from our building or facility. Okay, this is the very famous and basic one, but okay, how do you relate this demand with the damage? You should define a demand parameter with this performance objective. Are you going to use drift? Are you going to use rotation, cord rotation, plastic inch rotation, or whatever the member capacity or member type you use? It doesn't make sense, or it doesn't make much sense to have this so-called matrix. You should define, or you should relate it with your engineering parameter or demand parameter. But with the introduction, or with the performance earthquake engineering approach, the design or the check of the performance is related to a demand parameter. This time, this is not force, this is deformation. Or, okay, you define a damage state or a damage parameter, but what is its probability? You should also define its probability of exceedance to a damage state. And what's your expectation, or what's your criteria in terms of probability and the damage state? And of course, you need to define it with a so-called annual probability of exceedance. It's not just saying that with rare events you will have full operations, or in design-based earthquake you have life safety. What is your definition, and what is its probability? And you extend it with the so-called FEMA 356 concept. Up to performance-based design approach, engineers just focused on what is your demand, what is your capacity, and if your capacity is greater than the demand, you are safe. But again, one thing is missing. The demand that you are talking about is the median, and the capacity you are talking about is the median also. They have a distribution. In some cases, demand may be low. In some cases, it may be higher. Again, in terms of capacity, you have the same situation. There is a probability of failure that this cannot be achieved. And what is that probability? What is the probability of failure less than a specified amount? And in LRFT approach, what we do, we increase the demand and we decrease the capacity and try to find a kind of probability for a given failure in certain years. Most of the times it is the service life. But don't forget, everything that we are dealing has a distribution. And again, I want to state the problem in that sense. What is the probability of exceeding the performance objective in Y years? For instance, I'm aiming a immediate occupancy objective in 50 years. What is this chance to exceed that performance, not to achieve that performance? If I know that, I am more confident, or it makes more sense for me to decide, okay, this level is acceptable, or this level is not acceptable. But this is a complex and computationally intensive reliability problem. And of course, it needs a rigorous solving process. And additionally, the results are more dominated by the uncertainty of the earthquake input. This means that you should involve more ground motion input sets and provide more reliable solutions. But of course, this time you come up with the high analysis procedures, high analysis tasks. And of course, you need to uncouple the problem. You have a performance level. What is the chance of exiting that performance level with an earthquake with that probability of exceedance in Y years? In other words, what is the probability of exceeding immediate occupancy level for a 2% probability of exceedance in 50 years seismic event? This is one step further that it makes more reliable design, because you are talking about the service life and level of exceedance of the considered earthquake, and due to this earthquake, what is the exceeding of performance in a certain level of chance, let's say. Of course, probability, we use this while we are using this approach, we use probabilistic response spectrum, which is less conservative than the seismic in that region. We know that. That's why what we do, we develop a kind of calibrated load and resistance factors that I mentioned, and again using reliability analysis, or in very rare cases, Monte Carlo simulation, we can come with an appropriate overall reliability. What I mean is that if you increase the sampling numbers in your uncertainty, in our case, the uncertainty is the ground motion. If you increase the ground motion parameters or ground motion distribution, number of distribution that you use, of course, your reliability will get higher, and your results will make more confident at the end. But of course, it is a huge computational approach. Then our definition has the performance objective has painted three parts. One is what's the definition of that performance level, and what is the associated hazard, in which hazard level you are expecting to have that performance, and what is the confidence level that you are using? We all civil engineers, during our BS education, we all had statistical lectures or statistical projects. We didn't rely on that or pay attention for that lectures, let's say, but through our life we are using that procedures and the philosophy that is behind that lectures. But at the end, as an engineer, I can say that we have high, moderate, or low confidence to meet an earthquake with a certain probability of occurrence in a certain years. And you will say, okay, I will work with moderate confidence or high confidence or low confidence. Or for instance, you may say that 90% confidence our structure will remain stable with a probability of exceedance of 2% in 50 years. In other words, in 10%, the building may be unstable. As an engineer, you will decide, or you will say, okay, I deal with 10%. I'm satisfied with 10% confidence. But then other engineer may say 10% is quite high. I will go for 2%, 5%, whatever it is. But by doing this approach or applying this approach, you will come up with the consequence, and you will evaluate the consequence whether you will accept it or not. Because at the end, as an engineer, you provide the solution to a client or other professionals, and they don't understand drift, they don't understand plastic rotation, they don't understand base shear coefficient, or they understand the consequences. And I will just mention what maybe these consequences and whether they will accept them or not. At the end, this a little bit scary relationship has arisen. As a decision maker, whoever it is, or the contractor, investor, or the whoever it is who will give the decision, will deal with which intensity of earthquake, which parameter of your analysis, and what is the consequence. As an engineer, you know these, and you evolve all these parameters and say, okay, this is your loss, this is your consequence, whether it is annual loss or probable maximum loss or average annual loss, and whatever it is. But at the end, your decision variable is not something that you use in your previous so-called designs, like forces or deformations or other engineering demand parameters. It's something different. We are evolving something more different. And a new era has arisen as about 15-20 years ago, and this performance-based, it's all started with the assessment process, because we had so many buildings, existing buildings, old buildings, or even buildings that has experienced earthquake. What was their performance? What was do they need to be upgrade their performances, or are we going to demolish it, or are we going to continue to use them? this time, we had another tool to assess. We have the seismic demand, and consequent damage is estimated with a quantifiable parameters. Now, and we check it with the acceptable damage limits and say, okay, it is acceptable or not. But this time, again, we are quantifying the damage in different aspects. Like even we go to strains in some cases, concrete strain or steel strain, in other words, deformations. And we do it with a component level, which means that it's not a kind of global estimation, component by component, which means beam by beam, column by column, shear wall by shear wall. We do these assessments, we check this quantifiable damage, and check with the damage limits and say, okay, this component is acceptable or not. But this brings us to another issue or another approach, which is a nonlinear procedure, which is deformation-based seismic assessment concept. Now, we are not dealing with any linear approach or linear approach that try to predict nonlinear response with some parameters. We're directly using nonlinear analysis procedures. This time, we are trying to reflect the nonlinear behavior of the structure in a more reliable way. Don't forget, we are not trying to simulate what's on the site. We are trying to estimate in a more reliable fashion what's going on the site under seismic action. That's all. It's not real, but we know that it's more acceptable, it's more reliable, and we go one further detail or one further inside look to the structural response, structural behavior. Of course, we are going to use deformations. Of course, we are going to use nonlinear analysis, but at the end, again, we need to quantify our overall response to a more understandable or more known parameters with the public. A project which is called ATC 58 has been introduced in 2005, something as I remember. After a 10 years program, they developed the next generation. It started 2000, in 2015 something. The next generation design has been proposed to engineering society. And of course, it is inevitable that performance is expressed in terms of probabilities, but now these performance definitions are based on direct economic loss, which means that what is the ratio of the repair and replacement cost that the buildings experience, what is the casualties, the deaths or serious injury, and what is the downtime, which is loss of use. These makes more sense or more effective to tell the people, the end users, let's say, your design. Otherwise, even among engineers, the performance objectives defined in terms of engineering parameters doesn't make sense. But once you said, after this, I'll have a performance objective, which you will have 10% of your building investment cost. it makes sense to anybody, or a percent of the occupants will have lost their lives, or you will not use your facility for this duration. It makes more sense. That's why this approach has been introduced. But in order to apply this, there should be a kind of law paths or procedure that should be followed. And as the owner, the designer, the building official, or all parties should come together at the first day and select the performance objective first, which is accepted by all parties. And of course, a preliminary design, and check whether this design achieves this performance level. If not, go back. And if it is done, it is. But the more critical, and which is unfortunately lack in the engineering practice, is this phase, which means that the owner, designer, and everybody who is related with the project comes together at the first day and define everything at the first hand. But unfortunately, it's not the case most of the times. Of course, there are some certain projects going around that I'm involved, but generally somebody says something and the designer is involved somewhere here. Everything has selected and done. Nevertheless, this is the near approach. As I mentioned, it was 2018. A procedure has been introduced, the FEMA P58. This is a huge project. This is a huge document. It's not implemented in the practice now, but some research is going on how to implement it in the engineering practice. But the design criteria is defined based on different aspects, like what will the structural damage, non-structural damage, of course, casualty, financial loss, to be unsafe play card after an earthquake, what will the repair time? Now, one step further, what will be the environmental impacts? You considered all these, especially the non-structural and financial loss. Because this kind of approach leads us to insurance sector. Because starting from your house to any manufacturing facility, insurance is somewhere involved in your process. And from the design point, you define your, or you define your loss, financial loss approach, and depending on that, your insurance premium even changes. And of course, you need a board, as I mentioned. You need a board that should discuss everything and create the design, not just one group. Every group should be involved, because otherwise these aspects have different profession, different expertise, different parties that is involved in the construction process of the building, and even use of the building. You should have them at the first day. And at the end, that you should have a kind of quality check. And FEMA P58 provides a kind of guideline, even a tool, how to quantify these, because there are so many fancy definitions here. What will be the structural damage, non-structural damage, but how do you quantify it? How do you calculate the repair time? How do you calculate the impact, environmental impact of the loss? that document provides you a guideline, both in terms of their theoretical base and application. Even they provide a kind of tool. And what you have at the end, for instance, for different levels of earthquake, for different levels of non-structural components, like mechanical, electrical, exterior cladding, interior partition walls, ceilings, and others, what will be the repair time is required? And you may have an idea, totally you have 40 days, for instance, which component has the most effect on this? And which component is the critical? For instance, what is the loss? Total loss, and it's shared with different parts, different non-structural components. Again, do you see which component is the critical, both in terms of days, both in terms of economical loss? And of course, which component has the most contribution to the overall cost and loss? This type of approach is more effective to explain the contractor or the investor or the decision maker that your design is good or not, or what's your design's aim. Otherwise, they don't understand immediate occupancy. They don't understand life safety. What they understand is something they use in their daily life, which is money, or which is repair cost, or which is duration. Another approach, which is called the Resilient-Based Earthquake Design Initiative, has been introduced, a kind of framework to implement for achieving a kind of beyond code buildings. This is called READY system. It's a kind of rating system, which is similar, not exactly similar, but concept is similar with the LEED, which is a kind of environmental evaluation of a building. This is seismic evaluation of a building, and it has different design criteria for different aspects again. And based on the criteria, I will just mention a couple of minutes later, you will have a ready level in terms of whether it is a platinum, gold, or silver. This is not obligatory. This is some like LEED certificate the investors may ask, but just to give you an idea, what is platinum, what is gold, what is silver, they define a downtime, which is in other words, recovery day, which is the direct loss or occupancy safety criteria. These are very basic criteria, but of course in the document they have their details. And for instance, if you have a direct loss less than 2.5% and recovery day less than 72 hours, and physical injury due to physical building components unlikely in your occupancy safety, you have platinum. But once the functional recovery and loss increases, you go to gold and silver. But again, as you see, the seismic grading or seismic design performance again is based on not engineering parameters, not any engineering procedure or quantitatively defined in terms of deformations or forces. It is just time, money, and loss. I don't want to go that much detail, but as I mentioned, what is direct how you define the 2.5%? How do you define 72 hours? It is all detailed in the document. It's all free. You can download and check. Especially in very recent years, starting from 2010, the peer has introduced a kind of documentation and organized an initiative called Tall Building Initiative and released some documentation on performance-based design of tall buildings, especially in seismically prone areas like California, Turkey, or Southeast Asia. There are so many, Japan, of course, high-rise buildings are designed, and the investments are quite high in terms of money. They need, and that buildings are not, cannot be designed based on standard codes as like you design 5-story or 8-story building. These are very special buildings in all aspects: structural system, behavior, types of materials used, and so forth. A guideline for performance-based design of tall buildings has been introduced. Additionally, another document has also introduced by Council of Tall Building and Urban Habitat, CTBUH, and very recently, just 1 year ago, Los Angeles Tall Building Structural Design Council has introduced the most recent documentation. But don't forget, these are all guidelines, these are all documents that help engineers to design these kinds of buildings. These are not codes. And this documentation has been introduced first in 2007, and there was a consensus of practitioners. So this is an important issue because, as I mentioned, the designers should come together and come up with a consensus of, because there may be different approach, different philosophies, but these documents are consensus of practitioners that performance-based design should be applied on these type of buildings in high-rise buildings. There are in practice, of course, it's not the first time that people are designing high-rise buildings, but the practice and protocol for non-prescriptive design is quite major in China and Japan. Of course, in the western region of the United States, it is more developed because that part of the world is quite high in seismic risk, and applications are quite, number of applications are quite high also. Of course, again, as I mentioned, this is a non-prescriptive design, which means that they provide a kind of guideline to you, depending on your problem, depending on your structural system, depending on your seismicity, and depending on your performance objective. Engineer will provide his design, not just obeying the rules of this document, but of course his experience, his approach, and so forth. That's why this methodology allows design flexibility and other opportunities to enhance the building performance. And it's not like a checklist approach. Do this, check this, or once you check, follow everything on the checklist, you're done. More importantly, as an engineer, you need to have detailed knowledge of the building behavior. I'm talking about for about 1 hour. My emphasis is know your building's behavior under seismic actions rather than rules or criteria given in the codes. And once you know the building behavior, of course, your design will be more reliable, more cost effective, and of course, more efficient to satisfy the performance objective. Just to wrap up what is done step by step in a performance-based design of a tall buildings process, of course, you need you do not use the codified hazard maps. You need a site-specific hazard assessment for specifically performed for the location, considering all geological and geotechnical aspects like liquefaction, ground deformation, slope stability, and so forth. And of course, levels of shaking that you are going to use in the design. This means that there should be a kind of close collaboration with the geotechnical and structural engineer in the beginning, because the actions will directly influenced by the site conditions. And at the end, okay, we are going to make a site-specific hazard assessment, but in which approach? Are we going to use probabilistic approach? Are we going to use deterministic approach? Are we going to use a conditional mean approach? Or are we going to apply a site response analysis? Depending on the performance criteria, depending on the objective that you are expecting, the behavior you are expecting from your building, either will work. Again, you are going to work with an earthquake engineer, a ground motion expert to work and choose one and proceed. And what you are going to have is the target spectrum. Using all these approaches, you are going to have a site-specific target spectrum. Why? You are going to, because you have to produce a set of ground motions to be used in the analysis phase, and you will go through a scaling and matching process. That's why you need this target spectrum. I'm not going to go that much detail with the probabilistic or deterministic or conditional mean, but what I want to emphasize is that this step needs expertise, and you need to work with a ground motion expert. This is not something that anybody would do. Doesn't matter whether you are going to use probabilistic seismic hazard analysis or deterministic, which means a scenario approach. You may say that, okay, I'm going to design this building based on a specific event that is expected in its location. For instance, in our case, in my case, I'm living in Istanbul. We are expecting a major earthquake in Istanbul. The one say that I am going to design this building with a scenario earthquake that is expected in Istanbul. This is another approach. You may do that. Or you may have a specific building, and you may need to have the ground motion parameters with the response which is compatible with the response of the building, or in other words, at the response periods of the building that you are going to design, and you are going to make this selection and this scaling based on these criteria. Of course, it's just an example. you will have different results in different periods with different approaches, whether you are probabilistic, deterministic, or conditional. But don't forget, again, you are doing something probabilistic, or so the ground motion input is always have uncertainties. You accept an uncertainty, you accept a level of confidence, and you proceed. The second step of the design, you make a kind of linear analysis. What you do is just initial proportioning, which means that you make the analysis, you determine the orientation and the dimension of your proposed structural system. Depending on your approach, you may do it in a service level earthquake, design level earthquake, even in risk targeted maximum critical earthquake. It depends on your approach. But generally, what we do is we use the service level earthquake demands, and we make a kind of pyramid design. And some engineers may use, as I mentioned, design earthquake or risk targeted maximum critical earthquake. But again, this is a kind of approach. As a second step, you make your design. In your design, of course, you make, again, in the first slide I mentioned, you make some assumptions. You are going to analyze building with an approximate methods, which is, it doesn't matter whether it is linear or non-linear, it's approximate. You will make some modeling assumptions and analysis assumptions. Typically, what is used is a response spectrum analysis. Your material strength assumption may change from approach to approach. Which are you going to use, design strengths or expected strengths or characteristic strengths? Are you going, in terms of section modifiers, are you going to use crack section stiffness? But of course, depending on which level you are using, whether you are using service level earthquake or design based earthquake level, these approaches change. Of course, as I mentioned, Tall Building Initiative and Los Angeles Tall Building Seismic Design Council has some approach or some advices which to use. You may use based on your approach, whether characteristic or which modifier you are going to use. And you will make an analysis. You need a mathematical model of your structure. Of course, you need to model, of course, all lateral force resistance systems. In some approach, in some worlds, design procedure, some engineers model just the lateral resisting system, or they categorize their structural members like lateral system, primary gravity system, secondary gravity system, and so forth. But generally, what is done in practice, include in your model all lateral force resisting system, primary gravity system, and basements. Of course, since you are dealing with a high-rise building, P delta effects should be included. This is the approach, for instance, for service level earthquake, expected material properties, and more realistic stiffnesses, because we all know that reinforced concrete will crack. That's why we are going to, it is more acceptable and advisable to use crack section stiffness. Don't forget, after all these linear analysis, we are going to come up with a design, a so-called preliminary design, and we are going to evaluate everything with nonlinear response history analysis. It's a kind of verification process. And of course, section properties are a very critical parameter to be decided. And Application of these property modifiers have a significant effect on the member forces and deformations, of course, and engineers should be very careful which one to use. You see, depending on your structural member, even it differs from in each structural member, in plane or out of plane, whether it is basement or structural wall, coupling beam, and so forth. For each degree of freedom, you have different coefficients. As an engineer, you will decide this. It's not a rule again. You will decide. Of course, at the end, you model the structure and you have the mathematical model. You have everything in your structural system. And you need to have adequate amount of complexity in your structure. If you go more complex, if you want to model everything in your structure, get more complex, you put more complexity in your model, and you have the results may be problematic after all, because keep it simple as much possible, because it doesn't mean that you have more reliable results if you have every member in your mathematical model. It's a very important issue. Do it as it is needed, or it is adequate. Not go much that detail. That this time you do not control the results. Results control you. And of course, at the end, in order to have a more refined understanding of the building response, you need to make a nonlinear response history analysis, and you evaluate the deformations like in the plastic hinge zones. For that, you need a kind of approach how to evaluate the nonlinear behavior of your members. As for these high-rise buildings, core system is the major lateral load resisting system, and you need to refine your nonlinear behavior in your wall. As for shear, since shear is has a brittle failure mode, it is modeled elastically. But in case of axial and flexural behavior, we use fibers which has basically three components, which means that you have the reinforcement represented with dots here, red dots. We have unconfined concrete, which is the panel of the walls, and you have confined concrete, which is the end zones of the walls. Of course, you have reinforced fibers everywhere, and use a kind of independent backbone for each fiber. Depending on your fiber modeling, depending on your geometry, as an engineer, you design this so-called configuration, which will be what is the dimension of this confined and unconfined regions. But at the end, again, don't forget, you are the one who decide everything. Again, one critical issue is the coupling beams. Whether you have a coupling beam, how did they behave under lateral loads, and how we are going to reflect its nonlinear response. Here, often we use lump plasticity, but of course you need to check the coupling level, whether it is low, intermediate, or high coupling, depending on the geometry and their connection. There are some rules, checkpoints. Of course, at the end, you are going to have the components. If you are using lumped plasticity, the most appropriate or most acceptable regions is the end regions, for the plastic deformation. You may use elastic segments in between, but it depends on your, in some cases you may hinge, even you have a shear hinge. Again, as an engineer, you will decide, because you need to know how your structure behaves, and you try to simulate as best as possible in your mathematical model. Of course, you need a kind of force deformation relationship. Most of them are based on tests, and since we cannot, as an engineer, we don't like to use curved so-called relationships, we make them multilinear relationships. But again, and as an engineer, you are going to decide whether it's a wall, it's a column, it's a beam, it's a sorry, it's a link beam, it's a squat wall or not. What will be this deformation and this demand and this capacity and this deformation? You will decide it. So just as a last comment, or as a last approach, we are, as an engineer, as for these kind of methodologies, we need a basis of design. In most cases, in an engineering practice, again, we don't have a basis of design document, and that's why we don't have good designs at the end. First of all, you need the basis of design document. This is a very important document to be written or prepared by the designer, which code are you going to use, which methods are you going to use, what is the structural system, what is the design procedure, what is our mathematical model methods, acceptable criteria, and so forth. Once we write this document, we need to submit to a so-called peer-reviewed panel and have their comments. And this will just provide us gain time, and have more efficient designs. Because you make a design, you make some calculations, and the peer review panel says it is not acceptable. You go back and forth. But once you define everything in the beginning and ask them for their verification or for approval, then you go faster, more confident, and efficient. I'm not going to go much detail because I'm a little bit exceeded my time, but starting from your structural system, load path, and anticipated inelastic behavior, and if is needed, some seismic devices like buckling restraints or isolators or dampers, you need to write it at the beginning. What we are planning to do. And even you should provide a schematic diagram, what my structure will look like starting from the top to the foundation. Even you should provide them a detailed lateral load system and gravity system, and their connection, what is their interaction, how will the connections be like, what is the component that you are going to use. Of course, another important is the foundation. What will the foundation like? Whether you have basement and with a reference to the geotechnical report and geotechnical engineer. But you should do it in the first glance, the first step. The design basis document should know it. And what will be the codes you are going to follow in terms of national, and what will be the non-code documents that you are going to follow? What will be the software that you are going to use? What will be the exceptional documents? Sometimes the government may, the local municipality asks something, or even the investor asks additional request, and it may relate it, or it may affect your design. You should say that the first, and of course, you should provide a performance objective table, not only for the whole building, but for the non-structural components. Because, as I mentioned, now we will also consider the response of non-structural elements, their seismic mitigation, or in case of seismic action, their loss. And of course, starting from the first starting point, you will initially make a response spectrum analysis, and you are going to verify your design with nonlinear response history analysis. Of course, based on this the nonlinear response history analysis results, you may change your design, you may change your section dimensions, you may change your capacities and so forth. But nevertheless, the design has basically two components: preliminary design based on linear analysis, verification design based on nonlinear response history analysis. And since seismic design an iterative process, you go one to another, and at the end, once you satisfy all the acceptance criteria in terms of quantitative, not qualitative, quantitative parameters. Again, just to give you an idea, this is an example from the peer website. As you see, both the core system, which is the lateral load system, preliminary gravity system, and the foundation is all in the mathematical model, since foundation input motion is affecting the structural response. Of course, you will do the service level earthquake analysis, then maximum critical earthquake analysis, and check. And one of the, I don't want to go in detail, but one critical issue is that in tall buildings we are not accepting a high level of nonlinear response. That's why the damping is used less than 5%, and in general we consider it 2.5%. One of the missing, or one of the wrong application is that since code spectrums are 5% spectrums, engineers use directly from the codes and do not change the damping. And of course, 5% damping and 2.5% damping are quite different. That's why in the beginning they make a critical mistake. Of course, again, crack section properties are quite important. Of course, while using model response spectrum, 90% model mass participation is important. Of course, again, not only the building itself, but the non-structural elements such as claddings and wall partitions are also checked based on drift. And that's why for these kind of buildings, drift limits are quite small, like 0.5%. This is an example. I don't know how much you are involved in high-rise design, but once you make a preliminary design, 0.5% is quite achievable limit. It's not that much low, because we are all accustomed with 1% to even 2% limits in classical reinforced concrete mid-rise buildings. But once you go high-rise buildings, you control the lateral displacement, and 0.5% is not that low. In some cases, you need to control the deformation with different innovative techniques, like so-called outriggers. As you see, different levels, you provide some additional elements here, like braces or buckling restraint braces, depending on your design. And since this building is a little bit slender, you provide some additional outrigger elements. You see again, this is the gravity columns, lateral load resisting system were connected with the core. What you do is the outriggers with BRB elements. These type of applications are quite numbers are quite high, especially in high-rise buildings. Otherwise, it's not that easy to control the deformations. Right. To wrap up, I'm not going to go much this. I'm just coming to conclusions, because as I mentioned, it's almost finished with the time that I've been told by Mustafa. It's inevitable that the seismic design will be performance-based in the coming years. It's inevitable. And the criteria will be economical aspects, not the deformations. Coming years, in 1 decade later, we are going to talk about 10%, 2%, 5% economical loss for performance criteria. But again, we will, in order to have a more reliable design, it will be more probabilistic. Of course, it's due to its nature, as I mentioned, starting from the loads. The loads are coming from nature. This has a uncertainty. The material we use or we produce have uncertainty in strength. The loads, the analysis that we are doing has uncertainty, and so forth. And it's my personal conclusion or personal idea that we are going to make more reliability analysis in the future. We will have different scenarios, different inputs, different parameters, and we will have not just median values. We are going to use upper and lower bound properties, lower bound results, and we will evaluate them in a statistical and probabilistic manner and come up with the a kind of menu that has different results, and the end users or the investors will pick one, and we will more work on reliability concept in the coming years.
And I would like to thank to Dr. Tuzun for his great presentation. It was a pleasure for us hosting you today. And thank you all for attending and for your time. I hope you enjoyed the presentation. Personally, I will definitely go back and watch it again to digest all the concepts Dr. Tuzun have covered. So it was an intense session. But I would like to comment, especially as the modern seismic codes arrive more and more, inevitably we need to reinforce our knowledge on earthquake engineering and make ourselves acquainted with concepts and methodologies. That's obvious. In ProtaStructure, we had to implement different versions of the same code all over again. We are witnessing a constant change in these technologies as well. So the earthquake engineering is not stagnant, it's also progressing.
Yes.
It's no doubt that seismic design requires a special expertise, and that's the expertise we are delivering to our users with ProtaStructure. ProtaStructure is now capable of designing a building to code requirements. It can perform irregularity checks, structural checks, as well as ductile and non-ductile design, including Eurocode 8, UBC, IBC, FEMA, and Turkish seismic codes. Besides, ProtaStructure can assess the building performance by nonlinear static pushover or nonlinear time history analysis with OpenSea's integration, with all material nonlinearity automatically calculated and with all the detailed assessment reports prepared. So before ending the webinar for today, I'd like to get a few points out of the way. Our marketing manager, John, is on my neck to remind you that for those who are interested, we have special prices available globally for the attendees of this webinar. So when you invest in ProtaStructure, it will come with free annual maintenance, including all updates, maintenance packs, and professional support. And you will also have access to our e-learning and knowledge hub, which is online. If you want to continually hear about our updates and events, you can follow us on social media and subscribe to our news channel. And thank you all one last time, and stay safe. Hope to see you in another webinar.
Thank you, Mustafa. Well, hope to see you again. Bye.
Bye.